understand and we learn something. So let me remind you what we did last week. So we are dealing with what is called these extensive form game, and they can be presented with trees like this, and we introduce everything. And we have seen what is a pure strategy, and I use a notation AI for the pure strategy of player I. And the pure strategy for player I would be on each, let's say the red one is I. On each edge, starting from a red point, you choose one edge with a 1 and all the other one with 0. And the same here. This is a pure strategy. A behavior strategy is when you put some probabilities. So at these two edges, you put numbers between 0 and 1, but such that the sum is 1, and the same here. So these are pure strategies and behavior strategy. And the set of all pure strategies denoted by AI or BI for the behavior strategies. And when we take this into account for all players, so when we take A1, A2, A3, here we have 3 players, then it makes this set A, which is made of pure strategy profile, and this is a behavior strategy profile. And then we have seen that we can put a weight or put a payoff on each. Oh, by the way, A is included in B because it's a special case. But we can put a payoff on any behavior strategy by looking at the number we have associated with each leaf. Because when we take into account all these strategies, we end up with numbers on each edge. And if you multiply these numbers, you get a weight on each leaf. And this gives you a probability. It's an exercise. So we can give a payoff for player I with the strategy B by this formula. And what we have seen also is that, okay, this is for extensive form game, but we can define what was studied before, which is a strategy game by taking this set A, and I use the same notation for the pure strategies, and these payoff that we just computed, and it gives us a strategy game. And we have also seen that once you have a finite strategy game, you can find its mixed extension. And I told you it's very good in order to understand what is the difference between pure strategy, behavior strategy, and mixed strategy is you write everything and you will understand. However, if the game has perfect recall, and I introduce what it means you do not lose your memory. Then mixed strategies and behavior strategies can be identified. So you don't have really something new as long as you have this perfect recall, and this is a result which is called Kuhn's theorem. So I encourage you to do a small graph and try to see what are these objects. I also define a Nash equilibrium, and the weak point with Nash equilibrium in this context is that it doesn't see the dynamic. And there is an example where on the simplest graph, which is like this, so if one player takes this path, then the game is over. However, when we define Nash equilibrium, we also have to take into account what happens here, which will not happen if we take this, if we take this play of the game, but it's encoded in the Nash equilibrium. So it means this is not a very useful notion for this game. That's why we are going to refine this notion. Now, however, they exist if we have perfect recall. And one way to do something better is to look at subtree. I explain what is a subtree, and I explain what means that we can decompose a tree at a x. For example, you can decompose at this point x, and you get a subtree, which is everything from this blue point to the leaves. And you can also restrict the strategy, which means you end up with a subgame, which I called gamma x. The subgame is gamma x with a strategy. And then you have a notion of something better than a Nash equilibrium, which is called a subgame perfect equilibrium, where you impose a condition for all subtrees. So it's inside the set of Nash equilibrium, but it takes into account the dynamics already. And again, it exists if we have perfect recall. Then I quickly introduce this notion of weakly and strictly dominating strategy. It's not only related to this topic, but some students started using it, so I gave the definition. And one way to solve this game is what is called backward induction. There is an easy example. Oh, no, not yet. It's not on the website yet. But please, if you don't have worked on any example, this is also something you can do. Look at what is backward induction. There are many examples on internet. Now, this is good if you don't have too many, this is called the information set. If you do not have too many information set in your game, because you cannot decompose that information set. So it means this definition is good if we don't have too many like this. If we have too many, we cannot decompose. And so it means we are not getting anything interesting. So I need to do something else. And this is what I'm going to introduce today. Any question or remark? So the summary is we define Nash equilibrium. What is the best solution for this game? They are not very nice because not very efficient because they don't see the dynamic. Then if we can decompose, it's slightly better. But if we have too many places like this, and remember, a place like this means the player doesn't know if he's here or here. If we have too many places like this, then we cannot decompose, and this sub-game perfect equilibrium is also not a very good notion. So we need to do something better. And the point is that these definitions are quite natural. Once you understand them, you will see, oh, but yeah, it has to be like this. There is no alternative. So now we are going to deal with places like this. What can we do when we have something like this? Because we were not able to deal with this in the previous framework. So the idea, first I write the idea. What is a new idea is to, at information set, with more than one node, so like the one in yellow, at information set with more than one node or one vertex is the same, we are going to add beliefs. So we will add an information. I told you that the player doesn't know if he's here or here. We will add an information about his beliefs. Okay. And then, so we are going to add belief and compute. We are going to compute the new payoff according to the beliefs, according to. So of course, if you believe that there is 80% chance that you are here, only 20% chance that you are here, here you have some payoff. So you are going to change the way you compute the final payoff because you know that 80% chance you are here, 20% you are here. So we will take this into account. But first, I don't tell you how. And we are going to use, it will come later, what is called Bayes' formula or Bayes' rule. I guess that you have all seen such a formula. I just recall it. If you have never seen this, please don't ask ChatGPT, but ask Wikipedia, and it will tell you what is the meaning of this formula. So this is what we call Bayes' rule. The probability of A knowing B is the probability of B knowing A times P of A divided by P of B. Of course, P of B has to be different from 0. Who has never seen this? Is there anybody who has never seen this? Really? So Google Bayes' rule, you will see. Or yeah, I cannot explain it. It's about probability, and it's not difficult to understand. And it will become clear, in fact. I will use it, but we will see it. So let me give you a first definition in this framework. So we consider, I use the same notation, but I recall it. This gamma is an extensive form game. Okay. We have V, the set of vertices. I just recall it once. And we have L, the set of leaves. So remember, the leaves are the endpoint of this tree, or they are far away from this specific point, the root. Okay. So what is, in the definition, a system of belief? A system of belief the new definition is a function. I sometimes use the word map. It's the same. A map or a function, I use these two words. It's a map or a function which I denote by mu. This is mu. Mu from the set of vertices, but not a leaf. So I take all points which are not a leaf, and it takes value in 0, 1. So these are numbers between 0 and 1, satisfying one condition, that the sum of mu of x is equal to 1, but I have to specify for all x in omega ij. So on this picture, we have just one example. So I'm going to make a second example just to see. Okay, so now we have two information sets with more than one node. I need to put a function on all nodes, but it's really interesting on this information set, so that when I do the sum of these numbers at one information set, I get 1. So it means exactly, I suppose that I have 80% of chance to be here, 20% of chance to be here. Of course, if you have only one point in an information set, you have no choice. You have to put 1 because the sum has to be 1. So here it's 1. So that's why I don't care about this point. But here I have to say something. So I'm going to say that we have 50% here and 50% here of chance to be there. So this is what is called a system of belief. I believe that I'm at this point with a certain probability. I don't tell you yet how we are going to compute or estimate this value. If you have any question about the definition, you can just ask me. So this is a system of belief. And then still in this definition, so this is for we have to do it for any omega ij. Remember, omega ij, it's simply, if we have just one point, it's just one point, and here it is these 2 points. So it's an information set, but it's only interesting at these information set. And still in the definition, an assessment is a pair where you have V and mu, and what is B is a behavior strategy profile, and mu is precisely a system of belief. So please observe that these two notions, they complement each other. Because B, we have seen, gives you numbers on edges. B encodes the behaviors. It contains number on edges with a certain condition, while mu give you a certain value on vertices, and in particular on vertices which are on the same or inside the same information set. So they complement each other. There is no overlap. So mu is something new I've just introduced today. And now, given So this is the definition is finished. But given B on mu, so now if you give me a B on a mu, we can compute the probability that a leaf Z is reached. So I'm going to compute the probability that we reach this leaf. So let's assume too big. I'm going to concentrate on this leaf. So probability that we reach this leaf conditional to. There are three conditions. The first one is why ij has been reached. I will explain on the picture. The second condition is that inside this information set, we use, or the probability of x is given by mu x. And the third condition is that players follow B. Of course, I choose a B, I choose a mu, so in the following computation, I need to choose both mu and B. So what is the meaning, or what I'm going to compute? We have seen before that the probability, without this information, the probability of reaching any leaves was given by the product of the values on each edges. This is what we have seen last week. But now I have one more information. And so I'm going to compute the probability of reaching this leaf, knowing that I reach this information set, that on this information set, I'm going to use mu x, and then that I will continue with B. So it's very natural. And if you are familiar with these kind of things, you can already guess that the formula I'm going to write. So what is this probability? So I cheated a little bit because I said I consider this leaf and I'm assuming or I'm considering this set omega ij, but I could also have considered this set omega ij. And of course, if I reach this set omega ij, I have no chance to get this leaf, So if I assume that I'm here, the probability of reaching this one is of course 0. So how to compute this? If Z is a descendant, so it's, and this is the first picture I did, is a descendant of any x belonging to omega ij, I'm going to get then set, okay, my picture is a little bit too simple because I need at least one more step. Okay, let's do it. And now let's consider this one. Okay, so consider, I suppose that Z, this is a Z, is a descendant of omega ij. Then set gamma, or gamma of Z equal to, we have already seen this. It looks complicated, but it's not. The path, this is the path between x, so the first one is x, and the last one, I should write xm, the last one is z, and z. So in this picture, it's quite simple. I have only the first one, second one, third, oh, I shouldn't have used red, but doesn't matter. And third one. So this is a path from, x, which belong to omega ij, to z. Okay. So I may have more than just 3 points, but in this case, we have 3 points. And I set So now I said this probability Pij z b mu. Again, this is a probability of reaching z with these three conditions. And let's look at the formula time. The product of xj plus 1 from j is equal to 1 up to m minus 1. Why is this? If you know that you are in omega ij, so if you know that you are here and you want to reach this point, you need to take the probability that you are exactly at this point and not at this one. So this is a mu x, and then times the number on this edge times the number on this edge. Yes? Of course you can choose mu x is equal to 1, but it means you know that you are never at this point. But I need to take all z into account. So as I said, if I take a z here, of course the probability is 0. 0, I mean, if I consider this omega ij. Now, this one has a priori non-zero probability. This one has non-zero probability. This one has also non-zero probability, but it's not the same x. And this one has also non-zero probability. So this is a natural formula. But if you know me for some years, you should complain about this. What is the problem with this equality? I told you, when you have an equality, you should have the same variables on the left and on the right. There is no x on the left. Why? It doesn't matter. Why? You cannot blame me. Because, as Heavido mentioned, there is only one possible x. If you take this z, and it has only one grandfather. So it can only be this x. You have no chance that it is this one. So the information about x is in fact encoded already in z. So I don't need to write the x on the left-hand side. There is, given z, there is only one possible x, no choice. So this equality is fine. Okay. So this is again, this is a probability of reaching z, knowing that you are at omega ij. Inside omega ij, you take the probability of this x, and you follow b for the value on the edges. So it means, in particular, you can forget everything before omega ij. Okay. And I said, if z is a descendant, otherwise, if z is not a descendant of any x inside omega ij, then you can just set this probability Pij of z mu, b or mu first, b mu is of course 0, because if you are not a if you consider this z here, it's not a descendant of anybody in this set, you have no chance to reach this z starting from omega ij. And now exercise, which is too easy. So nobody has really to do it, but you can think about it. We again have a probability. So observation. The sum over all z which are leaves of Pij of z b mu is 1. Just think about it. And in fact, for many of them, it's 0. The contribution is 0. It's only non-zero for those who are descendant of omega ij. And this ij here means omega ij. Okay. And now the expected payoff. So the expected payoff for player I, conditional that precisely omega ij has been reached. So what is this conditional is, so I again need to put an ij to remember that I'm my omega ij, uij of b mu, because it depends on b, but also on the system of belief. You can guess it's now a sum over z belonging to L, Pij of zb mu times ui of z. So if you think about, I had a formula of this type at the beginning on the blackboard, but it was a different probability distribution because now it's conditional to something. It's conditional to the fact that I know I'm here inside this set. I put a probability of 0.8 to be at this point, of 0.2 to be at this point. So I can compute the payoff I'm going to receive, or the expected payoff, depending on this belief, 0.2 and 0.8. And B gives me the numbers on each, or the number on each edge. So this is a conditional probability. Any question about this? It's quite natural. So you should understand. Yes. Just think about, take an example, and you will easily understand it. You know, when it's conditional, it means you have one more information. Instead of not knowing at all where you are, and then you have to use the previous formula. If you know that you are somewhere here, and if you know that there is a probability to be exactly at this point and exactly at this point, then the probabilities of obtaining something here can be changed.
Profile for one player.
No, a profile contains all players because you're not sure that this edge is associated to this point. So this is if this point is for player I, this is for player I. But this could be for different player. That's why it's B and not BI. Okay, now let me just introduce one more thing. Let us set P. I haven't introduced this, but it's very natural. P of omega ijb. Remember, I introduced P of xb, the probability of being at x, knowing for the strategy B is simply the product of the edges. Now, if I put omega ij, it means I'm going to sum over all x belonging to omega ij of P of xb, which means it's, oh, sorry, I missed one page in my notes. Okay, wait a second. Yeah, I missed one page. Keep this for later, sorry. It's correct, but I need it in 10 minutes. Yeah, I introduced this formula and I missed one page. So we computed this expected payoff conditional to B with this formula. Okay. So I forget this. So once I'm here, I can do something. I can look for the best strategy in order to have I want to have the bigger payoff. So I can define, so according to what we have just done, so accordingly, we will see why I put this word. The behavior strategy BI which is an element of, so for player I, is the best reply. I already mentioned best reply once or two times, is the best reply for player I against the other B1, B2, B I minus 1, Bi, and Bn. So all the other one. It could be a definition, but so the best reply for player I against this and against mu at omega ij is given by, you will not be surprised, is given by the following formula. Bi is given by, or it's an element of argmax of Bi. So what it is, I computed this payoff knowing that we are at omega ij. Now, of course, suppose the initial payoff on many of them was 0 except 1, which was a big value. I want to take the strategy which gives me the biggest payoff. So if I'm the player I will choose argmax means I change, I need to put a dot. So I have this strategy for the other player are fixed. And for player I just put a dot because it means I just go over all possible strategies for player I. This is this notion of argmax. I go over all strategy for player I, and I take the one which gives me the maximum value. And this might be not unique. So that's why it's a belonging, because there might be two different strategies for player I, which give me a big number, the same big number. So this is this notion of argmax. I change, these variables are fixed, except this one for player I. I put all possible strategies, and I took the one which gives me the maximum payoff, conditional to the fact that we are at omega ij. That's natural. So if you are young and happy to be young, you don't have to remember this exact formula, but you should understand the idea. You change all possible strategy for player I, and you take the one which gives you the maximum value. And it might not be unique, so I cannot put an equality, but because equality would mean there is only one, maybe you have two strategies which give you the same payoff. So it's belonging. This is a set. Argmax gives you a set. Okay. So it's a natural definition. Yeah. And now I can give you, remember, my aim is to find something which is better than a Nash equilibrium. So the next definition, and we have introduced these beliefs, so I'm using them. And the beliefs in the definition, you observe here, I don't see the mu, but in the computation of this mu, there is a belief. So it's encoded inside this guy. So the definition, an assessment. An assessment, remember, is a pair B mu of gamma of this game is called sequentially rational. Of course, we are a rational player, so we want to increase our payoff if for any I, for any player, and any omega ij, bi, the strategy bi is the best. I just write the best reply of player I against the other one, B1 up to Bi minus 1, Bi plus 1, up to Bn. And mu. So far mu is given. So this is a completely natural definition. It means I'm going to look at the strategies which give me the best payoff. That's it. And I do this at every information set. So for every player, I do it at every information set. But in fact, the only important one is when we have more than one node. Because for the other one, when it's one, the system of belief is trivial. It's just one. That's it. So it's all this in definition is only important, in fact, for these two places. Is there any question? Oh, now I could hit it. But you observe so far, I didn't tell you how to choose mu. Nobody has decided how to choose why it's 0.8 and 0.2. So we are going to optimize this. We are going to optimize the choice of mu. And so now let us set P omega ij B. So now remember, we had a weight on each, a probability of reaching each x. Now, if we have in omega ij 2x, I just take the sum because the probability to be at one of these 2 points is the probability to be here plus the probability to be here. So that's natural to take the sum. And it means this is the probability that any x inside omega ij has been reached by the player, following B. So they follow the strategy given by B, because B gives me the weights on each edge. And now, it's again a quite essential definition. This assessment mu B is weakly consistent. It's a long word or long expression, but it's weakly consistent. It's weakly consistent with Bayes' rule. If I'm going to tell you what means this assessment is weakly consistent. Look first at this picture. I want to give a meaning to this 0.8, 0.2. I chose them arbitrarily. But we have already one number attached to this point, and one number attached to this point. It is this pxb. So I will use this information because I haven't used it yet. There is no relation so far between pxb and the 0.8 and 0.2 that I put here. So he says that it's weakly consistent with Bayes' rule if whenever there is just a condition, whenever P of omega ij B is strictly bigger than 0, one has that mu x is given by, I'm going to call it P. Please think about it. I'm claiming that this is completely natural. What is the meaning? So the first equality is, it's not an equality, it's just two different notations for the same thing. This is the system of belief, remember? And I want to give a number, or associate a number to it. And the correct notation is this P knowing omega ij of xp. So this has a meaning, and the formula is this one. Look, we had a certain number or certain probability to reach this point and another probability to reach this one. I divide by the sum of these two probabilities, and it gives me the probability to choose this one and the probability to choose that one. If I take the sum of this number at this point plus the number at this point, I obtain 1, because I'm just taking this number divided by the sum of these two and this number divided by the sum of these two. So if I add them, I just get 1. So this is the most simple, or the simplest way to decide a number or to associate this system of belief. Okay? So it's called weakly consistent with bias rule. And you observe, of course, this formula is meaningful only if P of ij be strictly bigger than 0. Otherwise, I divide by 0. But it means if I have no chance to reach these 2 points with the strategy B, then I don't have any reason to put any number here, because I will never come here. So that's why there is this condition, otherwise, which means if P of omega ij b is equal to 0, there is no condition, no need to, or no, let's say differently, no condition on mu x with x inside omega ij. I have no way to say which one should have a certain weight or not. So now I give you one way to compute these. No. This is only the system of belief. I'm not using payoff yet. We already introduced the payoff based on any mu. But now I'm finding one way, and this is where Bayes' rule is implicitly used, because in this formula, in fact, I use Bayes' rule.
Probability of the omega ijxp by that, and over here you defined it again with the sum in the middle group.
No.
Over xp.
Wait, the 2 points are on the left. It means I'm defining this guy, or this is just a notation, this guy, by this formula. And indeed, this one has been defined, this one has been defined, so I can define what is on the left, please. Okay, so before I had introduced what means sequentially rational, which means it's rational at every step where you need to take a decision. But this was independent of mu. It was true for any mu. Now I gave you a formula for finding the most natural mu. So let me keep this, the first blackboard. Because now if I take both this definition plus the fact that this is the best mu, I obtain a new definition. A weak perfect. These names are a little bit long, but a weak perfect Bayesian equilibrium By the way, I would be happy if other students also ask questions, not only one. So a weak perfect Bayesian equilibrium it's an assessment. So you need two information. It's an assessment mu B and mu, a strategy plus a system of belief that is sequentially rational, which is just on the left. And there is now a new condition, and weakly consistent. With Bayes' rule. I'm glad that everything is now on the blackboard, because this sequentially rational look was a definition on a condition on BI. But if you think about it, this definition of this condition on BI use the information on mu, any mu. And the second condition is weakly consistent. It's a condition on mu, but the condition on mu use B. So it's tricky to find this, because you have two conditions, this sequentially rational and weakly consistent with Bayes' rule, but one is for B condition with mu, the other one is about mu condition with B. So they are not independent. If you want to solve this problem, find this perfect Bayesian equilibrium, you have to write exactly these two conditions and find the best B and mu together. They are not independent conditions. Is it clear for everybody? Again, look at this definition. Here you have a condition on BI, but BI is the best reply, and the best reply is for given mu, for anyone, but it's given. This one is a condition on mu, but you compute it given B. So now if you have these two conditions, you have to solve this problem, or this one plus this one, and you find the best B and mu which satisfy both. So there are these two conditions, maybe I can write it. These two conditions, what I mean by two conditions, it's sequentially rational, and the second one is weakly consistent with Bayes' rule. These two conditions on B and mu, they are not independent. They are linked. So you cannot solve one and then the other one. You really have to solve them simultaneously. Not independent. Which is probably more interesting. Okay, what is the relation with Nash equilibrium? Remember, we had Nash equilibrium, they were not so good. I introduced this notion of sequentially rational, and now something even more complicated, but which contain more information. There is an exercise, but you can, okay, I put it as an exercise. Weak perfect. You just need to look at the definition. Weak perfect Bayes equilibrium are Nash equilibrium. So if you remember, we had a definition for Nash equilibrium. Let me just do a picture. We had, suppose this is a set of all Nash equilibrium. Some of them are not very natural because they don't take into account the dynamic. But now inside, we have this WPBE. Inside the set of Nash equilibrium, we have those ones which are better. But there are Nash equilibrium which are not weakly perfect Bayes equilibrium. But you observe there is still one weak point. No, nothing is perfect. I mentioned here, it was here, if P of omega ij B is 0, we had no condition. So it means this definition is good as long as this number is not 0, because if it is 0, I still don't know how to choose these two numbers. So we need to improve still a little bit. And this is the last step. There is one more notion that we have already introduced a long time ago. A strategy profile is completely mixed. Do you remember what means completely mixed? Maybe I didn't spend a lot of time on this. It's completely mixed. So in our framework, strategy profile, remember, is a way to put some numbers on edges. B corresponds to putting numbers on edges. But for example, a pure strategy would have a 1 and a 0. And when I mention completely mixed, mean I don't want to have a 0. So a pure strategy is never completely mixed. A completely mixed means I have no 0 anywhere. And why it's interesting to have no 0? Because remember, if we have no 0 anywhere, then this condition will not be satisfied. Because if we have no 0, there will always be a probability to reach this set. So I will consider strategies where this condition is not satisfied. And since this condition is not satisfied, it means there is a non-zero probability to be here. And what I constructed before give me an information. So if I consider completely mixed strategies, the condition on mu, I can give it everywhere. So a strategy profile is completely mixed if the probability of reaching any strategy profile B, let me call it B. Strategy profile B is completely mixed if the probability of reaching X following this strategy is always strictly positive. It's not 0. So we reach, I just write it in Word, we reach all vertices with a certain probability, a non-zero probability. So as I said, pure strategy is never mixed. And this is quite clear. The mix is opposite to, completely mixed is opposite to pure. And I'm going to give a name. I just invented BM for the set of all completely mixed strategies. I'm not sure that this is a standard notation. I decided to put M for mixed. I saw that some also are putting 0, but I don't think it's a good idea to put it. Good question. Do we have Bm is equal to B minus A. Who can answer this question? This is a set of all behavior strategies. This is a set of pure strategies. Do we have this? A video, it's an exercise for you. The answer is probably no. Why? It's easy to construct an example. Take 0, 1, 1/2, 1/2. This is clearly not pure, but this is also not mixed. No, sorry, not completely mixed. So you have the answer. So, but it's true that what is correct is that BM intersection with A is empty set. You cannot be pure, having only some 0 and 1, and simultaneously having no 0. It's impossible. Or maybe on one graph. If you take just this graph, maybe the intersection, that's trivial. Okay. So I define the set of completely mixed strategies. The next definition is a bit annoying, but if we understand the main idea, it's good. It's sufficient. First, there is an observation, which is something I just mentioned, observation. If B is completely mixed, then, as I just mentioned, P of omega ij B is strictly bigger than 0 because I reach every point. And this implies that mu B, not mu B. There exists a unique weakly a unique strategy, a unique mu, which is, so there exists a unique mu which is weakly consistent with Bayes rule. Can you tell me why I mention it? Why it's unique? Because remember, I had a condition which was fixed, except if this is 0. But if this is never 0, then what I had written before, the way to compute mu is given. I had a formula. Remember, the formula was probably mu of x is P of xb divided by P of omega ij b. So wait for a second. So if the denominator is never 0, I have this formula. It gives me mu x for all x. So it's unique because it's completely defined. Yes, Havidu.
Pi is not unique, so mu x cannot be unique.
It's for fixed b. Please think a little bit before you ask question. For given b, this guy is b, which is completely mixed. This guy is never 0. I can use this formula for all x, which means mu x is uniquely defined. That's it. So whenever we have a completely mixed strategy, I have no choice for this belief, this system of belief. And I will call it, because it's unique, we denote it, or we denote it by mu with a small index b, simply because once you have b, it's given. Whenever b is completely mixed, this mu is fully defined. So far, so good. And now it's a small definition. I told you it's a bit annoying. We say that B mu is consistent. It's not weakly consistent. It's consistent if there exist see, don't worry too much about this. If you are first or second year, you don't have to fully understand. A sequence Bn mu Bn with Bn, I will explain. So that it's an approximation. What I'm doing is just an approximation. So that B mu is a limit when n goes to infinity. Bn. So what does it mean? It's a bit annoying, but I decided still to present it. We introduced before what is weakly consistent with Bayes' rule, but as we have seen for guys which are not completely mixed, it doesn't fully define mu(x). It fully defines mu only under this condition. So I'm going to say now that this B mu is consistent if you can approximate it by some Bn, mu Bn, with Bn completely mixed, so mu is fully defined. And as I said, you approximate. So this B is just some numbers on edges. You can approximate them by a sequence of numbers converging to these numbers. Okay, so it's an approximation of this assessment with some assessment which belong, I should write mu Bn, with some assessment which are completely mixed. So you approximate something with elements which have a better behavior. Because if it is completely mixed, it has a good behavior. And you say that it's consistent if you can approximate by this. Yes?
One limit, but then limit in what sense is it limit for a vector? And then vector with a constraint that it must sum to one. What is this limit? What is the meaning of this limit?
Each entry. But in fact, they're all equivalent. You can take the maximum of the difference or the L1 norm, the L infinity norm, the L2 norm. It's finite dimensional.
There's also a constraint. It's not just any vector.
Yeah.
Any vector. A constraint.
Yeah, I agree. You have constraint. But at every step here, you have a constraint. And one is that P, X, or these guys are not zero. But you know that a sequence of non-zero number can converge to zero. But still, we say that it's consistent if entry-wise, it converges correctly. And everything is finite dimensional, so you don't have any problem. You can take any norm in L. We are in R power, blah, blah, blah. I don't know which dimension, but still, it's finite dimensional. No heavy do. I continue. Okay, so just keep in mind, it doesn't matter the details. If we have a completely mixed strategy, it means we have no zero on any edge. It's the best situation because I can compute a unique system of belief. I'm saying that it's consistent if we can approximate by such strategies. Okay. I did hesitate to present this, but I decided to do it. And now the final definition, what is called a sequential, this is the last one, a sequential equilibrium is an assessment. So it's always a pair because I told you we have this additional information. It's an assessment B mu, which is sequentially rational, sequentially rational, and consistent. And if I use the picture that I still have here, they are exactly here. These guys are here. I put the name here, sequential. Sequential equilibrium. It's not completely trivial because with this definition, you are not sure that you are inside Nash equilibrium. It's not difficult, but you have to check that you are inside this previous set. I wanted to give you this definition. Again, you have to look what means sequentially rational. I introduced it, and consistent is what is on the left. It turns out that this is a good notion. And if you think about, take a step back. The very first Nash equilibrium doesn't take into account the dynamic. So it's a weak information. Then I introduce one which was subgame perfect equilibrium. I introduced it last week. The problem is with subgame perfect, they did not deal with this set. So we introduce one more information, is this system of belief. And then system of belief can be arbitrary. But if we want to be coherent with Bayes' rule, we have to choose a mu according to a certain definition, and I end up with this weakly perfect Bayesian equilibrium. Okay. Still, it's not perfect because if a strategy does not go here, I have no information on this place, so I do something slightly better by an approximation, and I end up here. So keep this in mind. We try to refine this notion of Bayes equilibrium. Now I need to give you one or two existence results. Otherwise, you could tell me, oh, but it doesn't exist. But no, the point is on, so let me state the proposition. I need to say it. Every extensive form game, so every gamma extensive form game with perfect recall, which is a minimum information perfect recall, has at least one sequential equilibrium. So this is a result, of course, we need, because it means there is one among all Nash equilibrium, there is one which has these good properties are introduced. In the second statement, still in this proposition, just for consistency, the second, and you will see that it's fortunate and good. If B mu is a sequential equilibrium, the one I have just introduced, then B is also a subgame perfect equilibrium. You should feel relief with this second statement. Why? Because I introduced this notion of perfect subgame perfect equilibrium last week. And at that time, I had not done anything about this situation. now I improve and I did something which is quite coherent for this situation. And it turns out that the new equilibrium I have defined, this sequential equilibrium, satisfy what I introduced last week. So there are improvement. I don't know how to, this subgame perfect equilibrium, I don't know if they are inside here or if they are also outside. I'm not sure that all subgame perfect equilibrium, if they are always weakly perfect Bayes equilibrium or not. So I don't know if I should do this new set, if it is inside this yellow one, or if it also goes outside. I'm not sure. I didn't check this.
Apply also for when we have a zero also, we can have a subgame perfect equilibrium.
Yeah, but it's a limit. Be careful, there are limits. So, okay, I simply don't know if we are completely inside the yellow one or if we have also someone outside. But okay, it's not the main point. What is important is that the red one is inside the yellow one and inside the white one. The white one, the white set was introduced last week, and today we introduced the yellow one and the red one. Okay, I know it was a bit complicated. I really encourage you to work on some examples because, okay, the truth, I did this big picture, but if you have a graph like this picture, you can only have a finite number of Nash equilibrium. So it means it's not a big set. It's maybe 3 points, one more point here and one more point here. So you don't have a big number of Nash equilibrium. There are very few. So don't be scared by this big set. It's not a continuum of Nash equilibrium. These are just a few points. I really encourage you to look at one or two examples. This is how we really understand this material. Okay, so this is essentially the end of this chapter. So just a few final remarks. So I just want to mention extension for infinite graph or infinite trees are possible. So it means people have also studied when these trees goes to infinity. And then it's of course much more complicated, or what is called choices in a continuum. Is possible. So what do I mean by this? I mean, instead of choosing just two possibilities, you may have an infinite number, a continuum here. There are also games where, for example, you choose a number between 1 and 0, between 0 and 100, so it's a continuum. So choices is a continuum is possible, but again, we do not look at this. And then these games can be solved by what is called backward induction. I already mentioned this last week, and there will be a report soon, but you have also to work by yourself, and there are many examples on internet. The way we solve them is we use this notion of dominating strategies, and we slowly eliminate some trajectories or some play of the game, and we end up with only one. But we go backward, which is not surprising because look, this notion of subtree was also backward. You take a x and you look at the subtree generated by x, and then you move to finally to the root. So going backward is rather natural in this framework. There exists also a notion of forward extension or forward induction, but it's less used apparently. But if somebody wants to look, you can check it exists, and there are some examples. I checked what is called forward induction. So this is also a technique, but it's less developed. Forward induction can also be used. And who has taken the course on graph theory? A few of them, a few of you. In graph theory, we introduced the notion of acyclic graphs, which are not trees. I just do a picture. The difference is we have, this is a cyclic graph. So what you can see is it's not, in the notion of tree, we did not allow loops. But this is not a loop. Because if we respect the orientation, you cannot go backward. So this is not a loop. But nevertheless, you have two paths leading to the same point. So it's not what I discussed so far. But I was wondering, it's just a question of curiosity, is, because you know this definition for those who attended graph theory, can we do some game theory, or is it natural to do some game theory on this structure? Because the idea would be that you would have different paths for the same outcome. So it's quite natural. And I didn't check on internet, but you can probably Google acyclic graphs and game theory and try to find if it is useful. And if it is useful, or if you find one example somewhere, you can write a report on this. But yeah, it's probably if you have taken the other course. Or it's called digraph, because the di is for direction, acyclic digraphs. Okay, so we have studied, it's finished for this chapter. We studied these kind of games, which are dynamical games, because we follow a certain flow along this graph, and we have seen different notions of Nash equilibrium and some refinements. So my feeling is that all these notions are quite natural. If you look at the notes, of course, some parts are technical, but all the definitions are quite natural. This is a good point. Do you have any question? We still have 10 minutes, so I can even start the next chapter. Yes, Havidou.
Capital BF is a finite set, right?
No. Because look, you can choose all numbers between 0 and 1, except 0 and except 1. Yes, so it's a real, what is finite are always pure strategies, because it's only made of 0 and 1. And then with some combinatoric, you can compute how many pure strategies you have. But for behavior strategies or mixed strategies, you always have a continuum, because these are probabilities. So no, it's not a finite. Okay, so this is the end of chapter 3. By the way, if you want to submit a report, don't do it on chapter 1 anymore. It's good to move to chapter 2 or 3. Thank you. Okay, chapter 4. Now it's not going to be so long. Game with incomplete information. Incomplete information. I will tell you a story at the end of this lecture about this. Yes, a story. And be careful. This sentence is not very precise. It is originally different from games with imperfect information. But so imperfect information is what we have seen. This was the imperfect information. Why I write this? Because the way they are introduced, it's not the same thing. But at the end of the day, we can reduce incomplete information into imperfect information. We will not see this today, but next week. So they are introduced differently, but by a certain trick, you can transform these incomplete information into imperfect information, which means finally we will come back to something we have already studied. But it's not the way it is introduced. So let's start with the first section. I will not be able to do a lot, but it's called Model of Knowledge. I could have done it before, but it was too early. I mean, now we are more familiar with some tools. Model of Knowledge. And it's quite interesting. It's useful. In fact, it's only one definition. Useful for describing the information that each player has at the beginning of the game, at the beginning. Of a game. So far, everybody knew the same thing. Everybody had the same information. But now we will, with incomplete information, not everybody will have the same thing. And so this first definition will be useful for understanding this notion. I still denote by still n players, and the players are denoted by n, which is a set 1, 2, up to n. So the n players are just defined by capital N, which is from 1 up to n. So let me just write one definition. An information model for n players it's three things. I call capital I, it's a lambda, it's a family rho I, and it's tau I. So let me give you, this is capital lambda. This letter is rho. And this is a curly T, curly capital T. So I'm going to use these three letters. And what are these three guys? Lambda is just a set, a finite set. So in fact, we already know everybody. Lambda is a finite set. Every rho I is a probability function on this set. And 3, this curly T or Ti is a partition. of omega, of lambda, which means Ti is this union of Ti. So let me do a picture. And I told you, you already know everybody. So take a finite set. Take a set lambda with some numbers. Oh, sorry, some points. This is capital lambda. A probability is just a function on these points which sum up to 1. So for example, 1/2, 1 over, oh, it's going to be complicated. 1, 2, 3, 4, 5. 1 over 7, 1 over 7, 1 over 7, 1 over 7, 2 over 7, 1 over 114. And I don't know if it sums up to 1. If it doesn't, you'd correct it. Okay, it should sum up to 1. Oh, no, it doesn't. Okay, you correct me. So this is a probability. It sums up to 1. No heavy do, no question. It does? Oh, good. Okay. And what is a partition? Remember, it's a way to put some points together. So the player 1 will decide that these two guys are together, this one are together, and these two are together. So for example, this is tau 1, 1, tau or t 1, 2, and this is t 1, 3, while another player, the blue guy is going to say, no, 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 these two are together and all the other one are together. So the second player will call this T21, this T22. That's it. So finite set, each has, you can define probability function on omega. So each player has a probability, so he has a function on this, and you have a partition. Okay, so I will start again with this because already with this simple object, we can do a few funny things. Do you have any question? I encourage you to think about reports. Oh yes, what is the story? We haven't seen it today, but next week we will see a slightly technical thing. And I spent hours this weekend trying to understand two lines. I then learned that these two lines have been written by a guy who receives a Nobel Prize precisely for this subject, so it cannot be simple. But it turns out that these two lines in the book I'm following are not correct. And I look at everywhere on the internet, nobody provided a better answer. I mean, I couldn't find something better. So I finally wrote to the author of this book. There are 3 authors, but one is younger and you can contact him. Please, can you tell me if this is correct? Because it has no sense. And a couple of hours later, I receive an answer. Oh, yes, you are right. This is not meaningful. So it means whenever you find something which doesn't make sense, even if it is in a good book, you are allowed to doubt. You are allowed to ask the author and to say, it doesn't make sense. I can do something better. Don't forget, you don't have to trust always any big book or any reference book. If it is not correct, it is not correct. And all authors have mistakes. I'm not claiming that the book is a bad book, not at all. But precisely at this point, they did a mistake. They wanted to be more general than everybody else. And indeed, you cannot find another reference book which is so general, but they did a mistake. I will try to explain this next week. Okay. So
the authors of the reference book win Nobel Prize.
Sorry? No. The subject was defined